In this lesson, we're investigating nuclear fission and nuclear fusion. Our lesson objectives: first compare and contrast artificial versus natural transmutation, and then compare and contrast nuclear fission and fusion reactions. So far we looked at natural transmutation, which have reactions that have one reactant breaking down. So all of our radioactive decay is natural. It's a spontaneous breaking down of these radioactive nuclei. But we could speed up that process by hitting the atoms with a beam of particles, and this is going to decrease the stability of that nuclei and cause it to split or undergo fission. This is called artificial transmutation because we are artificially making it transmutate into a more stable nuclei. So how do we speed up these particles? Well, we can use particle accelerators. And so here's one, this circular structure back here in the picture. This happens to be the world's current largest particle accelerator, and it's actually located just down the road at Brookhaven National Lab. And it's the RHIC, which is the Relativistic Heavy Ion Collider. So doing a comparison between natural and artificial transmutation, natural transmutation is our radioactive decay. It always has one reactant, which is spontaneously or naturally decaying into a more stable nuclei and releasing, in this case, an alpha particle in this example. Artificial is going to have more than one reactant. So in this case, we have two reactants here, and therefore it's not spontaneous. We are making this happen using things like particle accelerators to bombard a nuclei with a particle and causing it to undergo nuclear fission, to split. So let's check your understanding. Can you differentiate between natural and artificial transmutation? Now let's look at nuclear fission. So this is an artificial transmutation, so it's artificially splitting a heavy nuclei into smaller fragments. And so you see here we have uranium-235, and using a particle accelerator we can bombard it with neutrons. It's going to absorb those neutrons and cause that nucleus to split into lighter daughter nuclei. And when it does that, it's going to release lots of energy and more neutrons. And the changes in mass that we see are proportional to the total energy changes. And we can verify that using Einstein's equation, which is E equals mc squared, where E is our energy and m is our mass, and c is the constant, which is the speed of light. So in a nuclear fission reaction, we can take a small release of energy and convert it to very large amounts of energy. And so looking at this even further, we see again, we take a heavy nuclei, we're going to bombard it with neutrons. It causes the nuclei to split into lighter daughter nuclei and further release of neutrons. We could also see that when we write out the actual nuclear fission equations. Again, you see the artificial having two reactants, and then it's breaking apart into these lighter daughter nuclei, and that further release of neutrons. And that further release of neutrons is important, but also can be catastrophic. And so when, for example, that uranium absorbs a neutron, it's going to rapidly split apart, releasing more neutrons, and this creates what is called a chain reaction. And so we can control that chain reaction in a nuclear fission reactor by using things like moderators and control rods. And so let's look at that. So here is the inside of the fission reactor. We have our nuclear fuel rods, and then we have our control rods, which regulate the absorption of neutrons, as well as in this case the cooling fluid, which is going to act as a moderator, which will slow down the neutrons. So if we're trying to slow down the fission process, we have our moderators, and if we're trying to speed it up and release more neutrons, we have our control rods. And this is going to be inside our fission reactor. And what the fission reactor does is it takes this energy released from the reactor core, from the nuclear fission reaction, and it's going to convert it to steam, right? So we're basically using that heat energy that's being released to create steam, and that steam is then going to spin a turbine, and that turbine is going to then create electrical energy. Well, what happens if we don't control those neutrons? We get an uncontrolled chain reaction, and this is going to be lead to a large amount of and very rapid amount of energy release, and this is the premise behind a nuclear bomb. The other type of nuclear reaction we have is a fusion reaction. So this involves the fusing of lighter nuclei to produce heavier ones. And so the most common example we have here is the fusion of isotopes of hydrogen to make helium. And this is what is taking place on the sun. And so if we're trying to fuse these hydrogen, in essence, we're trying to fuse protons together. And so in order to put those positive charges very close to each other, we're going to need lots of energy. So a fusion reaction takes a lot of energy to put together or fuse those nuclei, in this case to make helium. And so there's a lot of advantages for a fusion reaction, but there's also some disadvantages. And so why don't we currently have nuclear fusion reactors? Well, it would be great because they produce a lot more energy than a nuclear fission reaction. The materials are much more readily available. Like for that example with hydrogen, hydrogen is readily available, much more readily available than, let's say, uranium. We get less waste and less radioactive waste, and even more important, there's less danger because we don't have the chain reaction that's possible. So again, why don't we have these fusion reactors? Well, they're just right now too energetically costly. To fuse together those nuclei takes a lot of energy, and currently the models that we have to put too much energy in versus the energy coming out to try to fuse these together. And so it's very difficult to achieve currently, but there are a lot of people across the world that are trying to work on viable models for a nuclear fusion reactor. So we do have an example of a fusion reaction that we did develop. And so the bombs dropped on Hiroshima and Nagasaki, those were nuclear fission bombs. And the hydrogen bomb, which was developed later, is an actual fusion reaction, and it's initiated. So at the top of the hydrogen bomb is a fission bomb, and that nuclear fission, the energy being released from that is actually used to then start the nuclear fusion reaction. And so when we look at a comparison of the nuclear explosions, these were the bombs Little Boy and Fat Man that were dropped on Hiroshima and Nagasaki. And you can see the amount of energy. These are nuclear fission bombs, 15 kilotons and 21 kilotons. And then Ivy Mike, Castle Bravo, and the Tsar Bomba, these were all nuclear fusion bombs. You can see the massive increase in energy release going from kilotons to megatons. So let's check your understanding. Can you distinguish between fusion and fission reactions? At this point, you should be able to compare and contrast artificial and natural transmutation and compare and contrast fission and fusion reactions.